Good? Okay. So last week, okay, we talked about Voronoi diagram, right? We are going to extend last week discussion into two different problems, okay, today, okay. So in other words, okay, we are only going to finish this chapter, okay, today. I could have squeezed a little bit to include like more material in today's lecture, but I think because today is actually the last day of before the midterm, right? So it's probably not a good idea to rush the class anyway, because the midterm only cover up to this chapter. Okay, so anyway, so let's get started. Oh, one more thing to remind you guys. Okay, I already posted the homework 3 on the E-class. Okay. And the due date, because I posted it last week, which actually include like some exercise from this chapter, okay, that we are going, we only, cover like halfway, okay. But today we are going to finish it, and the due date will be next week anyway, okay, next Wednesday, which is supposed to be a holiday, right, for students. Okay, so, well, but anyway, you can submit it online, okay? And so, the TA, okay, I will ask the TA to return the graded homework 1 and homework 2 to you before the midterm. Okay, the midterm is 2 weeks from now, okay? I'll have the TA return the graded homework 1 and homework 2, but probably not the homework 3 as I told you guys last time, okay? So 所以记得那个第一、第二个那个作业要在那个之前还给他们。Better 来最好是下个礼拜结束之前就可以，好不好 ？Okay. Okay. So okay, back to the class. Okay. So obviously the problem we discussed last time, okay, last week, okay, is to utilize what we called beach line, right, to solve the Voronoi diagram problem for a given set of sites, okay. Those sites are points, right? Okay, but now, okay. In certain special cases, special application to be exact, okay, the site does not necessarily to be points, okay. A site could be either a point or a segment, okay. What kind of application has such a requirement, okay? For instance, okay, when you plan the robot movement, okay, the wall, okay, in the indoor environment, okay, the wall, okay, each wall can be, abstract as a segment, right? Line segment. I mean, from the bird view, each wall can be viewed as a line segment, which block the robot, right? When the robot moves indoors, it should avoid like hitting the wall, right? It should avoid hitting the wall. So, in some sense, okay, the robot should, when it moves indoors, it should go through the road that is most clearance, from the wall, right? To avoid hitting the wall, right? So for example, like if I'm a robot, and I know this is the wall, that is the wall, I should work in between, right? So that I can avoid hitting either the left side or the right side walls, right? So to go, at the center line, this center line, conceptually is the edge in the Voronoi diagram, right? If you treat like the wall, okay, for example, like the left side and the right side wall as sides, then you can imagine, okay, the Voronoi diagram, okay, in this case will be, there'll be a line in between, right, in the middle, and that line obviously is the best path for a robot, right? Here I'm assuming a robot is a round shape, it's a very simple round shape. Okay, so it doesn't have a direction. Okay, it doesn't consider, I'm bigger on the left-hand side, so I should go, a little bit leaning toward the right or something like that. No. We assume the robot is, what should I say, does not have any angle preference. Okay, so for problem like that, okay, as I said, the side obviously will be the obstacles indoor, right? So the indoor obstacles, can be modeled by the line segments, but probably not points. Obviously, in indoor environment, you could have, for example, like a pole, right? A pole, which can be modeled as a point, yes. But that's, after all, is not very common. In the indoor environment, you see more like walls or like, for example, table, right? Well, you can sort of treat the table as like a combination of some line segments, right? Okay, so you get a point. Okay, so it makes sense to extend the problem we discussed, okay, from the point sets, okay, to not only the point sets, but also the line segment sets. Oh, sorry, not sets, sides, okay, point sides and the line segment sides, okay. So, but one thing we need to be a little bit careful here, okay, is that, okay, we do not want to deal with line segments. We assume line segments are separated. Separated. When I say separated, they could be very close. They could be very close. For example, like this close. Like this close. Okay, you can obviously see this S1 and S2 segment. Okay, one of their endpoints are very close, right? Their endpoints are very close. So, but we do not want them to connect. Okay, we don't want the line segments to share the endpoint. Why? Because we want to avoid ambiguity. Okay, because this is the situation when two line segments share one endpoint. Okay, remember the definition of Voronoi diagram. Okay, it will try to the line, because of the definition of Voronoi diagram. Okay, the each point, okay, belongs to, what should I say, the side that is closest to it, right? But think about this. If let me make sure at least I can work to that. Because today I'm confined by the wire, so I probably don't use the whiteboard there. Okay, just the whiteboard over there. Okay, so you can see that. Okay, because these two segments share this endpoint, right? So let's take any point in this shaded region. Any point in this shaded region. Those points will belong to, well, either sides, right? Because it is closest to this point, right? This point, any point here, will be closest to this point. But this point is, it belongs to both this segment and that segment, right? So in a Voronoi diagram, when a point belongs to, when I say belongs to two, when it has more than one closed segment, that basically indicate that point is what? Is edge, belong to the edge in the Voronoi diagram, right? Okay, for example, so for example, like this point is, is closest to both these two sides. So this point actually, will trace out one edge, right? In the Voronoi diagram, because it is closest to more than one side, right? If it's only close to one side, it is part of that cell, right? But if it's closest to more than one side, then it will belong to the edge in the Voronoi diagram. So, but the issue is here. Any point in this dark region, they have the closest point is this one, is this shared endpoint. So, but because this endpoint is shared by these two segments, so which means, these points are closest to two sides, right? Okay, because each segment is one side, right? So they should all belong to what? Belong to the edge in the Voronoi diagram. That is why, okay, they are all marked, black. It's because they will be considered as, kind of like a very, very thick edge, right? But obviously, this is not, because we don't consider edge like that, right? We normally consider edge just a line, right? Not like a region. Right, so this doesn't look good. This doesn't look good. Okay, so in order to avoid this situation, okay, we just consider, okay, two sides. Okay, their endpoints could be close, but they do not share it. They do not share it. Same thing here. If you have, the endpoints to be close, but not, you do not share them, then you will find that everything will be fine. Okay, you don't have this issue. You don't have this issue because, if you try to draw this figure like a really larger figure of this, you will find that, any point, okay, except like only one line, okay, will be closest to this. Both points, and all the other points will belong to either one left segment or right segment. Okay. So, but once when we extend this problem to include the line segment sides, is the original solution still work? Okay. The beach line, okay, it turns out that, okay, it's fine. It's fine. Okay, you can see that, okay, this is an example, okay, for our beach line. You can see the L basically represent the same L. Okay, and in this figure, actually we have S1, S2, S3, S4, and S5. We have 5 line segments, and you can see that. Okay, we actually have like something similar to beach line, right? Something similar to beach line, and which can still be maintained in a left to right data structure, right? But of course, we need to discuss, this thing further, okay, in more detail, to have better understanding of this, this thing, okay. So, okay, there are 5 situations. Originally, we have only one situation. The new arc may appear, right? Okay, which is what? Remember? The side event. Remember when a side emerges from the L, right? When L encountered a side, okay, a point side, then it's going to break the original parabola above that side. Into 2, right? Into 2 pieces. Okay, so let's consider these 5 situations separately. Okay, if a point P is closest to 2 side endpoints while being equal distant from them, okay, and L, I'm sorry, there's a L missing. Okay, the scan line, okay, and the P is a breakpoint that trace a line segment. So this is just like what should I say? Kind of like it's kind of like well, it's not appear here, but the situation is actually very easy, very simple. Okay, so we have one side like this, we have another side like this, and now we have a point that emerge here. You can see that if they are equal distance, okay, to this line point and this L, then this point is going to be a break point that traces a line segment in the Voronoi diagram. Okay, so well, actually this figure has that, but it's just not very obvious. Okay, it's this one. It's this one. Because this point, you see, is has the same distance to this endpoint and that endpoint, as well as the same distance to this L. Okay? And because of that, okay, so this fulfill the first situation. So it will traces a line segment. So this situation actually is just similar to what we originally have, in the point sides. Okay, because the point sides are exactly like that, and because this is kind of like we just treat these 2 sides. Okay, because this the endpoints are closest to this point, right? So you just consider this whole side as one point here, the whole side here as one point here. Then the segment side becomes a point side. Okay, so the consideration is pretty much the same. Okay, as what we have discussed in last week. Okay, so hopefully this is not difficult to understand. Okay, but there are other 4 cases. There are other 4 cases that we need to consider. Okay. Second one, if a point P is closest to 2 sides interior while being equal distant from them and L, okay, then P is a breakpoint that traces a line segment. So what exactly is this? Okay, it's actually here. This one. Okay, it has, well, this is not, here. This one is. You can see the point here has, the point here has equal distance to this side, and to L, right? Okay, this is the second case. Okay, it is closest to the interior of the line segments, of different line segments, the different interior, different line segment interiors, as well as equal distance to the L. Then it will traces, it is a breakpoint, and it will traces a straight line in between these two sides. Okay? So this line is going to be part of Voronoi diagram to separate these two sides. Okay? So far so good? Okay? And the third case, oh sorry. Okay, if a point P is closest to a side endpoint and the side interior of different sides, okay, while being equal distant from them and L, the P is a breakpoint that traces a parabolic arc. So this is this one. You can see it is the equal distance to this one, as well as this point. So it's as well as the distance to L. Okay, one interior, one endpoint, and the same distance to L. So this is still a breakpoint, but this is very special because in the last week, beach line, all the result that we traces, to create the Voronoi diagram. Okay, I mean we will create like a bunch of line segments, and eventually it becomes like something like this, right? You can see all these are line segments, right? Okay, but I mean only the third situation. Only the third situation. Okay, it doesn't trace out a line segment. Okay, the previous two cases trace out line segments, but the third case trace out the parabolic arc, which actually is this one. Is this one? Is this one? Why is it parabolic? Why is it like a parabola? It is because this edge, if I call it H, okay, if I call it H in the Voronoi diagram, it has an equal distance to a line and a point, right? Remember, okay, for parabola, it has an equal distance to a line and its focus, right? So this is why, okay, when a point, has equal distance to the interior of a line and an end point, Okay, it is a breakpoint, and it's going to trace a parabola. This parabola is going to use this line, okay, and this point as its focus. Okay? So that's the first three cases. Okay? The last two is kind of very strange. Okay? The last two is kind of strange. Okay? If a point P is closest to a side M point, okay, the shortest distance is realized by a segment that is perpendicular to a line segment side, and P has the same distance from L. Then P is a breakpoint that traces a line segment. What exactly is situation 4? The situation 4 actually is this one. I mean, the description of situation 4 is complicated. If you don't understand, that's perfectly fine. It doesn't mean your English is bad. Okay, it's because those that description is just complicated, to say the least. Okay, okay. Let me first, make it clear. Case 4, case 5 involve only one side. Case 4 and case 5 involve only one side, and those situations are only available in the segment side. Okay, it's this thing. You can see. I mean, when you are here, you can imagine. Okay, this. This point. Okay, this is exactly like after this point. Okay, you have the same distance to this, the interior and the line L, right? Okay, maybe you have something else here. We don't know. But if it's the leftmost one, then this is going to be the result, right? But you can see from here to this point, this exact point. Okay, this is the point where this line change into a parabola. Okay, because after this line, after this point, okay, we are going to, this point will be closest to the end point instead of like the interior, right? Of this segment side, the same segment side, okay, the same segment side. So this is like the particular case, exact particular case, the breakpoint between this parabola and this line segment. Okay, so this thing, okay, is mentioned as a case 4. You can see a point P is closest to a side end point. The shortest distance is realized by a segment that is perpendicular to line segment line segment side, and the P has the same distance to L. So you can see that the distance from this point to this end point, okay, is perpendicular to this segment, right? Okay, the shortest distance is perpendicular to this one, right? That's what that English sentence means. And this distance is the same as the distance to this L. Okay, so it is a breakpoint. When I say breakpoint, the breakpoint basically means like in the beach line. Okay, for example, like when the beach line when the component is different, for example, from here to here. Okay, then this is breakpoint from here to here because the type is different, right? The type is different, so it is breakpoint. So this is like a very special case because in like in point sides, if you only have one point, you do not have breakpoint. You do not have breakpoint. Okay, if you only have one side, okay, there's no breakpoint involved, only one side. Okay, if all the sides are point. But in the line segment, okay, you have case 4. You also have case 5. The case 5, if a side interior intersects the sweep line, then the interior intersection is a breakpoint that traces a line segment, okay, which is a side interior. Okay, so this is exactly this is situation. You can see S2 intersect with L, right? So you can see that, okay, it actually traces this segment. So, I mean, the segment is part of the Voronoi diagram. Yes, but you can see that, okay, it's also going to create like two components in the beach line. Okay, and both components will actually be straight lines. Okay, so once you have a better understanding of these 5 cases, okay, then the algorithm of that we use to solve the point size Voronoi diagram, okay, the basic structure doesn't need to be changed at all. Okay, we just need to add more discussion to, I mean, more case to deal with. Okay, in the algorithm. Okay, and for each case, they can be handled, okay, in constant time. Okay, for each case, they can be handled in constant time. So it's not going to be an issue. Okay, one last note. Okay, in case 4 and 5, as I said, okay, they only involve one side, right? So, okay, the breakpoint does not actually trace an arc of the Voronoi diagram. Okay, because there's only one side. Okay, so you will include this in the Voronoi diagram, but it doesn't. It's not one of the arc in the Voronoi diagram. Okay. So this one, as I said, this is case 4, right? It also doesn't create like an arc in the Voronoi diagram because all the points here will be closest to the side S5 anyway, right? So they will all belong to this cell anyway. Okay. Okay. So if you agree with this discussion, then let's have a closer look at what should I say, like the whole process. You know, how a line segment will be processed when your sweep line, you know, go across that line segment. Let's have a closer discussion. Closer look at this. Okay. We will have to separate. Obviously, you know, in this case, we will have to separate the line segment. The upper endpoint and lower endpoint, right? Because the line the sweep line obviously will encounter the upper endpoint first, right? And then the interior, and then the lower endpoint, right? Okay, so let's have a look. Okay, so side event at outer endpoint should be handled, okay, differently from side event at lower endpoint. This is obvious. Okay, so let's look at like how this sweep line goes past this line segment side. Okay, so at an upper endpoint, okay, when your strip line encounter upper endpoint, an arc of the beach line is split into two. So when the beach line encounter the upper endpoint, all it can see from this new line segment is only that point, right? It's only the upper endpoint, right? So it has pretty much no different from a side, a point side, right? So it basically has nothing, different from a point side. So that's so basically, it also break, okay, the beach, whatever on top of that point, okay, the arc will be split into two. So this situation is just like where is it? Yeah, just like this. It's no different, okay? Because think about this. You can include line segments below this point, right? So it doesn't affect the case, the discussion here. So it's going to break this arc into two, split this arc into two, okay, because of the upper endpoint. Okay? And well, of course, as for how it is splitted, it depends on which one we are discussing. Because if it's most likely if it's the other case, the other places are also like endpoint of sides, the other sides, endpoints of the other sides. Then, okay, it's going to be as just like the point size that we discussed, exactly the same. But if it's if it happens to be interior of line side, okay, above the strip line, then remember the case 3. Case 3 is the interior and the endpoint, one endpoint. Okay, the first case, the 5 cases, the first case is, okay, 2 endpoints. The second case is 2 interior. The third case is 1 endpoint, 1 interior. Okay, so the situation involve 1 endpoint has case 1 and case 2. Case 1 and case 3. Okay, how it will be processed, it depends on which case we are talking about. Okay, but in either cases, it's going to break the upper arc into, split the upper arc into 2. Okay, so then in between, 4 new arcs appear. Okay, the breakpoints between these 4 arcs are of the last 2 types. Okay, so it later becomes something like what should I say? One of them is going to be this case. But it's a 180-degree reverse, okay? Okay, but unfortunately, we don't have that here. Okay, but one of them is going to be, because you have a parabola, but the interior, okay, if it does not involve the other side, it's going to be straight line. Okay, I probably should say the straight line will be something like this. Okay, so it's, if you don't have any other sides or what should I say? Let me see. We don't have a case. Here. This one. Okay, this one. you can see you have this is a parabola, or it could be a line if the other side is a point side. So that one, okay, it's going. You have a breakpoint here, right? This breakpoint is the same as this breakpoint, okay? Because you can see it has its closest side is this one, okay, and it has equal distance, okay, to this side, and the L, and the distance to the endpoint here is perpendicular to this line segment, right? So this one is the one that I was talking about, but it's like a 180-degree reverse, not exactly 180 degree, but you get my point, okay? So we have this case, which is case 4, and this case, which is case 5. Okay, you should have this, okay, and this, okay? So which will create actually 4 separate arcs, okay, separate arcs, and that's what we meant here. 4 new arcs appear, and the breakpoints between those 4 arcs are of the last 2 types. Okay, and at the lower endpoint, the breakpoint, okay, is that it is the intersection of the side interior with the sweep line. Which is replaced by 2 breakpoints of the 4th type. Okay, so you are going to have with a parabolic arc in between. So it's the last one is we have a case. Last one is this one. We have this is type 4, right? The 4th case, and then parabola is here. When the lower endpoint leave the sweep line, we have this one, and a breakpoint of case 4. Okay, so this is the, should I say, life cycle? How the sweep line, goes through the line segment side. Okay, kind of complicated, but they can, as I said, there are only this many cases. Even though, yes, you may feel it's a little bit complicated, a little bit overwhelmed by so many cases. But keep in mind, each case can be handled in constant time. Okay, so pretty much like you can keep the algorithm, because the algorithm, you can see the algorithm. This Fortune's algorithm, okay, we have a handled circle event, handled side event, and this handled circle event, right? So basically, the handled event situation, is described in a separate subroutine, right? And in this subroutine, we can obviously add more cases there, okay? And as long as the case you add does not increase the complexity, okay? Because each case we originally discussed, even including the circle event, including the line, the side event, those events can be handled in constant time, right? Now, even though we have more type of events, as long as each type can be handled in constant time, then pretty much it's just like we just add those descriptions in the algorithm, and we don't need to worry about the complexity. Okay, so which is good, because this means that we use this pretty much this almost identical the sweep line algorithm to create the Voronoi diagram for a set of point and the line segments. Okay, so you can see the algorithm remains the same, except more types of side events and circle events need to be handled. Okay, so in the case 3, when the breakpoint involves an interior of a line segment and one endpoint or one point side. Okay, remember I told you. Okay, that's going to create a parabolic arc, right? It's going to trace a parabolic arc. Okay, so I need to emphasize that. Okay, yes, the resulting Voronoi diagram may have parabola arc. Okay, but we are going to treat, I mean, because parabola, we deal with parabola arc. I mean, we can deal with them easily, right? Think about this. I mean, what is parabola? I mean, we just need to know the starting point, the ending point, and which line we used and which focus we use to create that parabola. Then we can pretty much recreate that parabolic arc, right? Okay, so basically you can still treat, okay, the parabolic arc exactly the same as an edge. Okay, remember eventually we are going to store the whole Voronoi diagram into a doubly connected edge list, right? So actually, I mean, here, I mean, we have to extend the definition of the doubly connected edge list a little bit, because in the original doubly connected edge list, we do not have parabola as edge, right? But now, okay, we can extend it a little bit, okay? I mean, to consider, okay, the parabola as edge. Okay, in this here, I mean, what I meant here is in the doubly connected edge list. But it should be fine. It should be fine. I mean, if you really look at if you really read the doubly connected edge list data structure carefully, you will find that, yeah, I mean, each edge, okay, we are going to store like 2 half edges, right? For each edge, we have 2 half edges. But as long as we know the previous edge and the next edge, okay, I mean, the edge itself doesn't have to be straight, right? That's the point. That's the point, okay? That's the point why we can extend the doubly connected edge list to include the edge which are actually parabola, okay? So the algorithm will still have the same time and storage complexity, okay? It is because, as I said, as long as each event can be handled in constant time, then the discussion of the complexity and the storage basically, I mean, remains the same. This is like I mean, it shouldn't be a surprise to you guys, right? Okay, and then, okay, once you understand that, okay, now we are in a position to talk about, okay, say we are able to create a Voronoi diagram for an indoor environment, okay, and we treat like those walls, those obstacles as the event, the sites, okay, as the sites to create those Voronoi diagrams. So how we can, you know, use that to do the robot motion planning. Okay, so you can see that here, okay, in this particular example, we have how many? 1, 2, 3, 4, 5. We have 5 different segments, right? Inside this room, okay. And by the way, we actually also include, okay. We also actually include like the bounding box, the 4 sides in the bounding box, okay, into consideration when we create a Voronoi diagram. Okay, because we treat these 4 sides in the bounding box as wall as well. Okay, so to be exact, okay, in this particular example, we actually have 1, 2, 3, 4, 5. Okay, we actually have 9 segments. Okay, we actually have 9 segments. And just want you to know, the blue line indicate the Voronoi diagram, okay, for these 9 line segments. Okay, you can of course check like use a sweep line to see like you know how, I mean, they are created. Okay, but I will skip that. I will skip that here because now I'm going to focus on how, once you create this Voronoi diagram, how do you plan your robot movement? Here, of course, we model the robot as a circle shape, okay, as a disc, okay. It's kind of like a, you know, I don't know if you have used like a Roomba. You do know Roomba? You know, there's a small robot that clean the floor for you. You'll go like different places to clean the floor for you. I mean, it's round shape, right? It's round shape. You can kind of, you know, imagine this is a small Roomba. Okay, Roomba. I mean, in US, okay, Roomba is the biggest brand for those like floor cleaning robot. Okay, so everybody call those things Roomba. Okay, but anyway, okay. So now, okay, obviously, okay, you are given a start point and end point, right? You will be given a start point, end point. Okay, so say this is a start point, and this is the end point. Okay, and then, okay, what happens is like this. You first try to create a Voronoi diagram for these segments. Okay, so once you have that, okay, remember your robot, because it's a round shaped robot, right? So you know the radius of your robot, right? Okay, and by the way, for each point on the Voronoi diagram, okay, each point, for example, you can measure, you can obtain the distance to the closest side, right? This shouldn't be difficult, right? Okay, for example, for this point, the closest distance to the nearest side will be either this one or this one, and it can be computed very easily, right? Okay, so you are going to first, okay, if there are certain age which has like whose closest distance to the side, okay, is less than r, is less than the radius, then we cut it. Okay, we will cut it. Okay, so for example, here we have an edge that goes through here, right? But we will not include this edge. We will only include this edge up to here, but not here. Why? Because the robot can never move to those places, right? Once it moves to that place, the obstacles, I mean, will block its movement, right? Okay, the robot just cannot move to those places. Okay, for the similar reason, you are going to remove this edge because it's too narrow, right? This is too narrow. Okay, you remove this, you remove this. Okay, and after that, okay, you try to, I mean, you still have like all these edges, right? You still have all these edges. Okay, so then what happens is that, okay, you first move the beginning, the start point, okay, to, away from the nearest edge, okay, to the edge in the Voronoi diagram. In this case, you move, up to go to the edge in the Voronoi diagram. You move to here. And you do the same for the endpoint. Okay, you move away from the nearest obstacle, nearest line segment. So you move to this, right? So from here, if you are able to go from here, this point, okay, I mean it's like when I say move, I mean like you move the center of the robot to here, and you move the center of the robot from here to here. Okay, so if the center of the robot is able to go from this point to that point, we will be good, right? We will be good, right? And then, okay, starting from here, okay, you treat each edge, okay, as what should I say? A node in the graph. If two edges are connected, okay, you consider there's an edge in between. Okay? So obviously it's going to be a graph, right? It's going to be a graph. So we want to go from, because remember I told you I treat this one as a node, right? So I want to be able to traverse from this node to this node, right? So I can use any traversal algorithm that I want. I can use depth first search, I can use breadth first search, I can use, either of them. As long as I can go from this node, the node represent this edge, to a node represent this edge, I'll be good. Why? Because, well, I mean, if I can go from one node to another, that means they are connected, right? Okay, and I already removed the part that this robot cannot go through, right? Okay, for example, I mean, because I get rid of this one. I get rid of this one. Get rid of this one and this one as well. So these three edges, they are actually not connected. Okay, even though they look, we have them in the Voronoi diagram, but obviously this robot cannot go past those, right? So we will remove actually this one, probably not here either. So maybe this one. Okay, so that's the basic idea. Okay, so the robot motion planning can be done in this manner. Okay, so basically, I mean, we treat the edges, the arcs in the Voronoi diagram as the paths with the most clearance. So the robot basically go, follow the arcs in the Voronoi diagram. That's the basic idea. Okay, here is the retraction. We call this algorithm as a retraction algorithm because, well, we will retract the robot to, from the nearest line segment to the Voronoi diagram. So this is, we retract a little bit, and we'll retract not only the start point but also the end point. So that's why we call this algorithm retraction algorithm. But the basic idea is what I just described. And because obviously, think about this. Because I treat the edge as a node, right? How many nodes do we have? How many edges can we possibly have? It's linear, right? It's a linear to the number of sides. We proved that earlier, right? Okay, and we actually even remove some edges, right? We remove some edges. So number of nodes, I mean, should be linear, right? And then, okay, I mean, they may be connected, but we are going to use traversal algorithm, right? Either depth first search, breadth first search, but the number of the complexity of the traversal algorithm is bounded by the number of nodes anyway, right? Okay, so basically, I mean, this retraction algorithm, okay, complexity is not any more complex than linear. Okay, the most complicated part, okay, is in the creation of this Voronoi diagram. Okay, because it takes, as I said, n log n amount of time. Okay, so given n disjoint line segment obstacles and a disc-shaped robot, okay, the existence of a collision-free path between two positions of the robot can be determined in n log n time using linear storage. Okay. Oops. It's already 10:05. Okay, I'm sorry. Okay, so you get an idea. Okay, so this extension of a Voronoi diagram can be used, I mean, for this robot motion planning. Okay, so if you have no problem with this, okay, let's take 10 minutes break. When we come back, we are going to discuss the second extension of Voronoi diagram. Okay.